Okay, in our last lecture video, we figured out that we could take a molecule, and the example we were working with was water, and we could figure out just from the chemical formula that for any water sample we had, it would be 11% hydrogen and 88% oxygen. So we did that math. So it would stand to reason that if we can go from the chemical formula of the molecule to its percent composition of the individual elements that compose it, then we should be able to go from the individual percentages of the elements that compose it back to figuring out what the chemical formula is of that particular molecule. So in these examples, we're going to go backwards and determine chemical formulas given percent compositions of their individual elements. So in this video, we're going to do part 1, and the example we're going to work with has carbons, hydrogen, and oxygen in its chemical formula. But what we don't know in this chemical formula are the subscripts. We don't know how many carbons are there, how many hydrogens, or how many oxygens. What we know is the percent composition of each one of those elements, and we know that from some experiment that somebody did, right? We're not going to worry about that right now. But from their experiment, they figured out that this unknown compound is 39.99% carbon, it's 6.71% hydrogen, and it's 53.28% oxygen. So we want to go from these percent compositions to figuring out how many carbons, hydrogen, and oxygens are there in our chemical formula. But in this first step, in part 1, we're just going to figure out the ratios of the elements. So by ratios, we mean for every carbon we have, how many hydrogens do we have, and how many oxygens? We're not going to figure out exactly how many carbons, hydrogens, and oxygens do we have in this first part. We're just going to figure out the ratio. We're going to go through some steps. So the first step you do, so step 1, is you assume you have 100 grams of your sample molecule. Okay? And this is just to make the math easy. So right now, we know percent composition. We know the percent of carbon, the percent of hydrogen, and the percent of oxygen. But to figure out the ratio of the elements that are in this molecule, we need to get to totals of each atom, or at least moles of each type of atom. So we're going to start, though, with mass. So we're going to make an assumption that we have 100 grams of sample. So if we have 100 grams of sample, and that sample is 39.99% carbon, then we must have 39.99 grams of carbon. Okay? So again, if we have 100 grams of sample, and that sample is 39.99% carbon, then we must have 39.99 grams of carbon. And the first thing we'll do is convert that to moles. Because when we're working with chemical formulas, we're never in mass. We're always in units of moles. So we know that for every 1 mole of carbon, we have 12.01 grams of carbon. So our grams of carbon cancels out, and that leaves us with 3.3297. I'm just going to put a bunch of dots here because I got a lot more numbers on my calculator. I don't necessarily want to round it off because rounding kind of makes these problems a little bit more difficult. So you want to keep as many numbers as you can. This will be enough to keep for now for me. So we're going to do this calculation for every one of the element types in our chemical. And we know how many moles of carbon that we have. And 3.3297 moles of carbon. So we're going to divide everything, all of them, the moles of carbon, the moles of hydrogen, the moles of oxygen, by the moles of carbon because it was the smallest molecule. So we had 6.71% hydrogen, which means in our 100-gram sample we have 6.71 grams of hydrogen. So we want to figure out how many moles of hydrogen we have using the molar mass of hydrogen. So our grams of hydrogen cancels out. So in our 100-gram sample, we have 6.6567 moles of hydrogen. And then we'll do the same calculation for the oxygen, which was 53.28% mass composition of oxygen. So using the molar mass of oxygen to convert that mass of oxygen to moles, we get 3.33 moles of O. So now we know in this 100-gram sample how many moles of oxygen we have. We know how many moles of hydrogen we have. So in our next step, step number 2, is that we know that formulas, when we're looking at ratios of elements, we look at the subscript in a chemical formula. It's never a decimal number. It's never a fraction. It has to be a whole number. Right now, all of our values for moles here are in decimals. So to get rid of the decimal point, in step number, so we had 3.33 moles of oxygen, 6.65 ... moles of hydrogen. Right here, again, the moles of hydrogen by the moles of carbon, that also gives us of our calculation. We are going to first divide every single amount of moles, every number of moles that we just calculated, by the smallest number of moles. Smallest. There's 2 T's in smallest right now. Smallest number of moles. In this case, it was the moles of carbon. So let's go back and take a look at. So if we do that, we get, since we're dividing by moles of carbon, we get 1 mole of carbon. If we divide the mole, we get 1.999 moles of hydrogen, which is essentially 2. Right, so 1.9999 can be rounded off to 2 moles of hydrogen. And then if we divide 3.33 moles of 1. So 1 mole of oxygen. So now we've got whole numbers. And you notice that right now I said step A is to divide by the smallest number of moles that you calculated. Now sometimes doing that doesn't give you whole numbers. So we'll do another lecture video where that's the case and you have to do a separate additional calculation to get whole numbers. But in this case, dividing by the number of moles in the smallest value gave us whole numbers, so we're done. We have whole number ratios now. So we know in step 3 now we can write a formula for our compound that tells us the ratio of the atoms that are present in our formula. So we just figured out that there was 1 carbon for every 2 hydrogens for every 1 oxygen that we have. So if we were to write a formula for that, it would look like this. 1 carbon for every 2 hydrogens for every 1 oxygen. Now this is the empirical formula. It's not the true formula of our molecule. It only tells us the ratio of the elements. It doesn't tell us how many exactly of each element we have. It just tells us the ratio. So for example,